This is on page 403. We're continuing on these last couple problems. All right, here is some given information that tells you where the center is, so that's really helpful. It tells you where one of the foci is located, and it tells you the length of the major axis. So what I would do is start kind of sketching for yourself what pieces of information you have. You know that 0, 0 is the center, and you know that one of your foci is at 3, 0. So that actually tells you a lot of information. What direction does the major axis have to go? The major axis is going this way, right? Because the foci are always on the major axis. So if you wanted to sketch the rest of it, you'd also have a focus here. And then it's telling you the length of the major axis. The length of the major axis is 10. So that tells you that the vertex lies out here at +5 and the other vertex lies out here at -5. And I'm not sure yet where that minor axis is going. But I know that my center's at 0, 0. I know that my C value is 3, and I know that my A value is 5, right? Because C is center to focus, and A is center to vertex. So you're going to have to use the Pythagorean identity to solve for B, right? Because in your equation, you need to know what B squared is. Let's write our equation so far. If the center's at 0, 0, we can actually write the whole framework of the equation, right? X squared plus y squared equals 1. I don't have to go left or right. I don't have to go up or down. And if I know that this is a horizontal ellipse and A is 5, what number goes under x squared? 5 squared, which is 25, right? So the only thing in the equation that I'm missing is the b squared value. So I have to use the Pythagorean identity for an ellipse. A squared has to equal b squared plus c squared. Hopefully you recognize this is going to be a Pythagorean triple, right? Because I'm going to have 25 equals b squared plus 9. So b squared has to be 16, right? Right? B is going to be 4 because it's a 3, 4, 5 Pythagorean identity. B squared in my equation is 16. So you've got to figure out your center, figure out your A and B value in order to write that equation. Yep. Why is 25 the denominator? Because in this equation, x squared over a squared is going to be the general form. So anytime you have a horizontal ellipse, the a squared value goes in the denominator for x. A is the distance from the center to a vertex. So 5 is equal to A. And in the general formula, A squared is located in the equation. So maybe when you see another example, you'll see that kind of it's the same arrangement again. All right, so this time, okay, great. They show you the centers at 0, 0 again. So you could actually write out the framework of your equation, x squared plus y squared equals 1. We just have to figure out the denominators of the ellipse. So let's plot kind of what we know. We know 0, 0 is the center. This doesn't tell us if it's major or minor, but it tells us one of our 4 vertices is located at 0, -3. So if that's a vertex, there's also a vertex up here at 0, +3, right? It's symmetrical. All right, so now what does this word mean? The semi-minor axis has a length of 2. That means half of the minor axis. That is your B value then, right? Half of the minor axis is the distance from the center to a vertex. So it's telling you that B equals 2. Well, what is this distance? This distance is 3. So if this distance is 3, this must be the major axis in this direction, and this must be the minor axis in this direction to 2. So this is actually a vertical oriented ellipse where A is 3 and B is 2. So in the y direction, if we're going 3 units, we need to put a 9 underneath the y squared because that would be A squared. And if we're walking 2 in the horizontal direction, 2 squared is 4, so we're going to put a 4 under the x squared, right? So you take the square root of this number, and that's how far you walk away from the center. You take the square root of this number, and that's how far you walk away from the center to find your vertices. So you have a squared and b squared in your equation, and you need a and b on your graph. All right, and then here's a different word that you might not have seen before. The center is at 3, 5, and it's tangent, meaning the ellipse is tangent to both of the axes. What does tangent mean? You might not have really studied that in geometry, but tangent means it just touches it at a single point and it doesn't actually go through. Have you ever heard of a tangent line? That's what you're going to find with derivatives, tangent lines, versus a secant line. What? Oh, so there's tangent lines that just touch it once, and there's secant lines or chords that touch it twice. Maybe you've heard that from geometry. So if I'm going to sketch this ellipse at 3, 5 is my center. 1, 2, 3. 1, 2, 3, 4, 5. There's the center of my ellipse. If it's tangent to both of the axes, that means it's just going to touch it at that one point and kind of continue on its way. So it's going to kind of look like this. Its center is at 3, 5, and it's tangent to both of the axes. It doesn't cut through them. It just touches it at one point. I want you to try to write that equation, and I'll see in a minute if you can get it. So you got to think about, how do I shift my center? Right 3, up 5, so that has to be part of your equation. And what am I going to write in the denominators for a squared and b squared? So how do I go right 3, x minus 3 squared? How do I go up 5? Y minus 5 squared, right? So write your center first, write it equal to 1, so you know that it's an ellipse. And then this distance is 5, and this distance is 3. So horizontally, 3 squared is 9. Vertically, 5 squared is 25. So there's a lot of information packed into an equation. It tells you where the center is, the orientation, vertical or horizontal, and how far to go to mark your vertices. So we're going to practice that more with that book work and when we talk about some applications. Okay, the other thing I wanted to talk about today is eccentricity, because it deals right along with the ellipse equations, and it's how scientists are able to compare mathematically different orbits or different ellipses. So eccentricity, without a graph on hand, how would you explain to someone else how elliptical something is? So if we're looking at these, this should say A, B, or C. I mean, B is obviously the most elliptical, A is the most circular, but if you weren't even looking at the graph, could you tell from an equation how elliptical it is? Or could we quantify the difference between these two ellipses? How different is their eccentricity? Have you ever heard of the word eccentric? Have you ever said, I don't know, like maybe in a show that the neighbor is always like eccentric? They're like the crazy cat lady who walks their cat at 2 in the morning or something like that. You know what I mean? Eccentric, a little bit odd. So eccentric deals with the ovalness, right? A circle is kind of referred to as that kind of perfect shape. So the ellipse is a little bit odd compared to a perfect circle. So eccentric, it's an adjective in real life, but it's a mathematical quantity for an ellipse. So it says in figure A, the ellipse might be easily mistaken for a circle. In a circle, the foci are both located directly at the center. Therefore, when the foci are extremely close to the center, it's difficult to make a visual distinction between a circle and an ellipse. Early astronomers had a difficult time studying planetary orbits whose foci were relatively close to their centers. Now we can use the concept of eccentricity. Eccentricity of an ellipse is given by this ratio. You take C and divide it by A. Basically, it's how far is the foci from the center compared to the length of that major axis, right? C and A deal with the focus and the major axis. C is the distance from the center to a focus, and A is the distance from the center to a vertex of the major axis. For an ellipse to be very circular, we're going to come back to this, but for an ellipse to be circular, the eccentricity is 0, right? It's not odd. It's not eccentric. So like 0.01, that's pretty much a circle. Whereas for an elongated ellipse, the foci are close to the, this should be, say, close to the vertex. Sorry. For an elongated ellipse, the foci are close to the vertex, and the ratio is going to approach 1. So here, right, you've got your focus way out here. So let's say that your A value is 9 and your C value is 8. 8 divided by 9 is really close to 1. Whereas up here, right, your A value might be 9 and your C value might only be like 1. So then you've got 1/9 as compared to like 8/9. So it's depending on how far that focus is from the center of the ellipse. So let's calculate the eccentricity. If I gave you this equation, if you didn't graph it by hand, could you tell me how elliptical it is? So I don't have to worry about the center. All I need is A, B, and C. Right? Right now I have A and B. Oh, shoot. Maybe I printed it before you wrote these in. So why don't you write down ellipse A, x squared over 9 plus y squared over 4 equals 1. All right. We need to calculate C divided by A. That's how we quantify eccentricity. I know my A value already. What's my A value for this ellipse? 3. I take the square root of 9, the bigger number, and I get 3. So I need to calculate what C is using A squared equals B squared plus C squared. Right, so 9 equals 4 plus C squared. You're going to solve that for C. So to solve that for C, you'd subtract 4 to the other side and take the square root of both sides. So you'd have 5 equals C squared. So the square root of 5 is equal to C. So your eccentricity on your calculator, we have to calculate it out. See what that decimal is. So you're going to do the square root of 5 and divide by 3. Square root of 5 divided by 3 is an eccentricity, if we round it to what, 0.75 is what I got. So I took square root of 5 and divided by 3 on my calculator. I got an eccentricity of 0.75. Do you think that's pretty elliptical or pretty circular? Well, let's read. If the eccentricity is close to 0, it's a circle. If the eccentricity is elongated close to 1, it's an ellipse. I would say 0.75 is closer to 1 than it is to 0, right? You can't be 1 because you'd be a straight line. So 0.75 is closer to 1. I'd say it is elliptical. It's elongated. To compare these two, we need the eccentricity for ellipse B. Sorry that didn't print. X squared over 20 plus y squared over 15 equals 1. See if you can calculate the eccentricity for B. So you're going to find C and then do C divided by A. So is it 0.5? Because C is the square root of 5 from my Pythagorean. I subtracted 15 and took the square root. And then A is the square root of 20. It's not a perfect square, so I just left it as radical divided by a radical. Came out to a half. So which one is more eccentric? Ellipse A is more as an exaggerated oval, but B still has, it still is elliptical because 0.5 isn't 0, right? So it still has some slight eccentricity. All right, so the last piece, I'd like you to try the back two problems, finding the eccentricity of each ellipse, 1 and 2. And okay, so you should have paused the video and tried these two problems, example 1 and example 2. So now I'm going to show you the answer, so pause the video. All right, so I got A is 50, B is 14. When I plug that into the Pythagorean identity, I get that C is 48. So my eccentricity for the first example is 48 divided by 50. 0.96 is very close to 1, so it's very elongated. See how it is elongated. You can see that from the graph. All right, and then example 2, I got that A was 4 and B was 2. So when I solve for C, I get C is the square root of 12, and the square root of 12 divided by 4 is 0.87. So that's as far as we did today on the notes, and you are to do the book assignment under Tuesday night on your agenda on conics and ellipses. The book work is due Friday, and we're doing a quiz Friday on ellipses up till this point. So Thursday in class, we're doing applications that are not on your quiz, and Friday, we're doing a quiz on graphing, finding eccentricity, writing equations.